Hello chat, my name is Yusuf and this is my lab report on our first lab on constant velocity. For the introduction, what was the purpose? The purpose of this experiment is to observe and analyze the motion of an object that moves at a constant speed in a straight line. Using the video analysis software Tracker, we extracted the object's position as a function of time from a recorded video. By comparing the observed data with a computational model based on Newton's second law, we aim to verify the accuracy of the physical model in predicting real-world motion. So the goal of this is to demonstrate that the object's motion can be accurately described using fundamental principles of physics. The model used in this experiment is based on Newton's second law of motion, also known as the momentum principle, which states that the change in momentum of an object is proportional to the net force acting on it and the time that the force is acting. In our predicted model, the object's momentum, and thus velocity, remains constant as there's no force acting, no net force causing a change in motion. And here's a preview of our main results. The predicted position model shows a perfectly linear relationship consistent with an object moving at a constant speed. The observed graph closely follows the predicted model at the start, but starts to plateau at the end until it finally stops. This deviation can be attributed to external factors such as friction and air resistance, which we will discuss in detail at the end. Now for the experiment. So our system was the cart, and its surroundings was the track and the earth. The initial conditions were the cart was placed on a horizontal track such that the net force and thus the velocity change in the vertical direction is zero. The cart was pushed in the horizontal direction such that its initial velocity was 1 meter per second. After the initial push, the cart was allowed to run for a total of 3 seconds. The position at different times was recorded and plotted using Tracker. Now for the code. Up here, we initialize the ball, the trail, and the origin. The ball is the cart and its position. And then we initialize the plots for both the position versus time and velocity versus time, though we'll only be looking at the position versus time in this experiment. This initializes the ball's mass. This initializes the ball's initial position, initial velocity, the initial time, the time intervals that we want to record data at. And down here, we're basically updating it as long as the time is under 3 seconds. We're updating the graph such that it adds the new velocity to the initial velocity. So that's the change in the final velocity is equal to the initial velocity plus the F net over mass, which is the acceleration, times the change in time. And the position is equal to the initial position plus the velocity at that point times the change in time. And this adds the time together to make sure that the experiment progresses. This adds the trail to the graph to make sure that everything's displaying properly. Then this plots the position curve, this plots the velocity curve, and then we print everything. Here are the models that we got. This was the predicted model that shows a linear relationship, and here is the observed model, which closely follows that at the start, but starts to deviate from it as we progress, showing that there are forces acting on it as the slope does not remain constant, and thus the velocity does not remain constant. So why does this happen? In the computational model, the object's motion was assumed to occur in a frictionless environment with constant velocity. Since no forces were acting against the motion in the model, the predicted position over time resulted in a linear relationship, as shown in the green line. In reality, forces such as air resistance and friction act against the motion of the object. Air resistance creates drag force that reduces the object's speed over time. As you can see, the slope gets less and less. And incorporating air resistance and friction into the model would provide a more accurate representation of the object's motion. So for the conclusion questions, if I were to flip the x-axis, nothing would change except for how the graph is presented. Right now I chose the left direction, which is the direction that the cart was moving, to be positive. This creates a convex shape as the cart starts with a large positive velocity and starts to slope off. By flipping the x-axis, a concave shape would be created with the cart starting with a large negative velocity, becoming less and less steep until it flattens out. Both graphs would start off with a large speed that gradually approaches zero. Though I did not observe a zero net force because of friction and air resistance, I can still say what forces were acting on the cart. In the vertical direction, there was a force of gravity and normal force of the track canceling out to zero, resulting in no acceleration in the vertical direction. In the horizontal direction, there was only the forces of friction and air resistance, resulting in acceleration in the direction opposite of motion, causing the cart to slow down. Thank you.